All right, today's lesson is on mass defect. I think something that you'll find totally shocking. So you're probably asking yourself after learning about nuclear decay, where does the energy come from? If you consider the parent nuclei in this animation, it's just sitting still, kind of hanging out, chilling. After the nuclear reaction, it emits an alpha particle that comes off with a certain amount of kinetic energy. And presumably, when it spits this alpha particle off with this energy and this momentum in one direction, it should probably, in theory, recoil a little bit in the other direction. So the question becomes this: where does that energy come from that gives this, as well as the parent nuclei, or the new daughter nuclei, I guess in this case, its energy? If this was a bullet gun example, the bullet would have energy in one direction, traveling this way with some high speed, and it'd have a certain amount of kinetic energy. The gun would recoil in the opposite direction, and it'd also have a certain velocity, and therefore it'd have a certain amount of energy. And if I asked you, well, where does the energy come from in this example, you would say from the gunpowder, from whatever it was that you ignited, the chemicals that were in the bullet before the explosion took place had energy. That energy turned into the kinetic energy of the objects. And that's great. But there's no gunpowder here. There's no chemical fuels powering this nuclear reaction. So the question becomes, what is the form of energy that we started with that now is in the form of kinetic energy after the reaction? Well, turns out that if you look really carefully at what you started with in this nuclear reaction, so you start with this parent nuclei, maybe it's uranium. And then you get the daughter nuclei and some product, some radioactive decay product like an alpha particle. If you consider the mass of the parent and the combined mass of the daughter nuclei and the alpha particle, the law of conservation of mass would say that your mass at the beginning equals the mass final. But it turns out in this nuclear decay, the mass of the products, shown in here as this large nucleus and this alpha particle, are lighter, that's why the scale is up here, than the mass of the parent nuclei. So in the end, we are missing mass. According to the law of conservation of mass, should be the same before and after, but it is not. After numerous careful uh, measurements, we always find that in a nuclear decay, the parent nuclei is heavier than the products. So how do we resolve this? How do we answer this riddle, or how do we solve this apparent discrepancy between a fundamental law of physics, the law of conservation of mass, and the fact that we seem to be missing mass here? Well, logic would say, well, you just look closer, you're probably missing some mass somewhere. Maybe there was another little particle that went firing off somewhere, and that's where the missing mass is. But you're going to have to be more creative than that. You're going to have to be as creative as Einstein himself when he solved this problem. Because Einstein proposed and theorized that mass is just another form of energy. Now, you've all heard of the famous equation E equals mc squared. And what Einstein said is that any form of mass has an energy equivalence. Just write this out. Try and spell it right. Equivalence, you know what I mean. In other words, mass is a form of energy. And so in a nuclear reaction, when you start with a large nuclei, the parent nuclei, and it turns into another pretty big nucleus, not quite as big, and say in our previous example, an alpha particle. So if you take your parent nuclei and you turn it, or it turns into a daughter nuclei plus an alpha particle, Einstein would say you don't expect the mass to be the same, because in this reaction, you also produce energy. It's the kinetic energy of the particles moving off in this case. And so Einstein says, no problem. As long as you consider the mass of the parent nuclei, put that on the scale over here. And then on this side, you put the daughter nuclei's mass, you put the alpha particle's mass, and you consider the energy, which has a mass equivalence as well. So this energy also is a form of mass, and mass is the form of energy. As long as you add up those three things after, they will be the same as the parent before. And so, time to let the cat out of the bag. Until this point, you've learned about two fundamental laws: conservation laws, conservation of energy, where we say, well, the energy before and after any reaction, before and after any process should be the same. You just have to look for all forms of energy. And we have this law of conservation of mass. We're going to replace that thinking. It's not two separate things. We have the law of conservation of mass energy. So again, probably the best way to think about it is the way Einstein would have said it. He says that energy and mass are not necessarily two separate things. They are different forms of the same thing. So mass is a form of energy. Energy is a form of mass. Deal with it. Now, on that note, I'm going to take it one step further. So we see an example, and like I say, this is not a theory that's yet to be disproven or something like that. Every time we see a nuclear reaction, we always have this mass that's missing at the end, and it's always the equivalent. It's always the same as the energy that's being produced in that nuclear reaction. So this idea of mass energy equivalence is not a yet to be disproved theory. It's a fact of science. Now, we can also explain two other concepts then that we should understand. One is mass defect and binding energy. And again, listing them separate kind of makes them sound like separate things, but you'll see they're really interrelated. So let's talk about the definition first of all, the mass defect. Mass defect is this idea that when you put a nucleus together, and so down here we have a form of hydrogen called deuterium, and deuterium happens to be hydrogen with one proton and one neutron. The assembled nucleus, the deuterium, is lighter than the parts. In other words, if you looked at a single proton and a single neutron and you added up their masses, now I'm going to get to this in a minute, but instead of using kilograms, because kilograms are so large in terms of the scale of the proton and neutron, we'll use another, it's called an atomic mass unit. In terms of atomic mass units, you can see mass of a proton, this amount, mass of a neutron, this amount. If you add them up, you'll get a certain amount, but if you compare that to the nucleus itself, it only has 2.014 atomic mass units. And so the assembled nucleus is lighter. That's where the missing mass is showing up. So the mass defect, sometimes called delta M or mass defect, is really the difference between the mass of the assembled nucleus and the mass of the parts of the nucleus. So we call that the mass defect. Now, the binding energy then is this energy right here that is released in this kind of process when you convert some of the mass that you started with, the missing mass is being converted to the form of energy. And so we get the equivalent of the missing 0.002 atomic mass units. So again, if you want to look at the numbers, you add these up, there's more mass here than there is mass here. The missing mass was converted to 1.8 mega electron volts of energy. And so the binding energy is, if we think in reverse, it's the work done to take apart a nucleus. So consider a nucleus that is already together here. Imagine we want to take this apart, so we start pulling apart these particles that are held together by the strong nuclear force. You would have to put in some effort. You'd have to do some work. So we'd remember, work is force times distance. Every time I grab one of these with my little atomic tweezers and pull it apart, I'm doing some work. So that means I'm adding energy to this system. If I do a joule of work on the system should increase its total energy by 1 joule as well. And this doesn't show up in the form of energy. It shows up as this greater mass. So this process on this side, the binding energy diagram we have here, is really the reverse of this side. Here, we are adding energy. to increase the mass. Over here, we are losing mass to release energy. So you can see how mass defect and binding energy are really related. And they're related again by Einstein's equation. He would say the binding energy, sometimes called delta E, is equal to your mass defect times the speed of light squared. E is equal to mc squared. So moving forward, keep in mind that in nuclear reactions, not in chemical reactions, not in everyday interactions between matter, but in nuclear reactions, it is not, well, it is common, it is the norm to have energy created because of a loss of mass. And on a nuclear level, when we start putting together nuclei, when the universe puts them together, there is always kind of this conversion of mass to energy. And if you ever want to find out when you lose mass, how much energy did you produce, you use Einstein's equation, and vice versa. If you want to find out how much energy it would take to change the mass of something, you can use the same equation. By the way, in the equation, let's just give myself some room here. When it's E equals mc squared, E is energy. We can use, although I'm going to use probably joules in this class. You may see other forms like electron volts is handy to use as well, but we'll probably stick with joules because we don't have a ton of time. Mass is in kilograms, although sometimes you'll see it in AMUs. I'll give you an example of that just once to see it. And then C is our good old speed of light. And that's 3 times 10 to the 8th meters per second, that constant. So really only 2 variables here, E and M, that are related through this speed of light squared. Now, if we're going to do calculations involving mass defect, binding energy, and any energies released in nuclear reactions, then we got to get a little more precise than our standard 3 significant digits. So since mass defect, binding, and all these things are very slight on our normal scales, let's take a closer look at what really is the mass of a proton. We've been saying mass of proton and neutron is 1.67 times 10 to the minus 27 kilograms. Let's get a little more precise about it. So henceforth, when necessary, I mean, 3 digits is great for most calculations, but not for nuclear reactions. So mass of a proton, MP, 1.6726 times 10 to the minus 27 kilograms. Mass of a neutron, a little bit different, a little bit heavier, 1.6749 times 10 to the minus 27 kilograms. And if we ever have to use an AMU, an atomic mass unit, AMU, then it will be 1.66054 times 10 to the minus 27 kilograms. And again, big reminder, carry all digits for these calculations for sure. We are talking about things that are really extremely small. So if you don't keep, all your significant digits, if you don't carry all your numbers in your calculators, even a small rounding will affect your overall answer quite a bit. So let's look at an example question. This one has us calculating the mass defect and the binding energy for lithium-7. We just need one piece of information, and that is when you put together lithium-7, the mass of lithium-7 in atomic mass units is 7.16003 atomic mass units. So when we're asked about the mass defect, we're really finding the difference between the assembled nucleus and the parts of the nucleus. So let's start by finding, I guess, the first thing, which is what is the mass of lithium-7 in kilograms? Let's get that first of all. So lithium-7 in kilograms. So the mass of lithium-7 in kilograms, mass should be 7.016003 times 10 to the, times the atomic mass equivalent of that in kilograms. 1.1650, oh shoot, sorry, 1.66054 times 10 to the minus 27 kilograms. I'm going to warn you, there is a lot of numbers with a lot of digits, so we're going to run out of room here. I might do some erasing later on, and probably one of the biggest challenges, if you're anything like me and you already saw it, is I start to lose track of the numbers. So it's kind of a good idea to have like a piece of scrap paper, write down all your stuff, don't have to go back. It's nice to have a little more sophisticated calculators going for you so you can always go back and look at your values. But I'm pretty sure the mass of lithium-7, according to this atomic mass unit, or this mass given in kilograms, should be 1.16503536. I'll hold on to a bunch of digits just to play it safe. Kilograms. So that's my starting point. Now I want to find out the mass of the parts of the nucleus. So mass of, there's two things that we're going to consider. The mass of 3 protons, and we're going to consider the mass of 4 neutrons. It's lithium-7, so that is what the constituent parts of lithium-7 is. 3 protons, 4 neutrons. So in the case of the 3 protons, it's going to be 3 multiplied by the mass of each of those protons, but not from your periodic table, or sorry, not from your data sheet, but that precise number that I gave you. Oh, by the way, if you're working through problems with me, that number is in the footer of your booklets, just for quick reference anytime you need it. So 3 protons is 3 times 1.6726 times 10 to the minus 27 kilograms. And so when you multiply that out, you can check, but I think the answer is 5.0178 times 10 to the minus 27 kilograms. Mass of 4 neutrons should be 4 multiplied by 1.6749. Well, that's a 49 times 10 to the minus 27 kilograms. So 4 neutrons multiplied by the mass of each of those neutrons, and you get 6.6996 times 10 to the minus 27 kilograms. So a little sloppy, but don't trust me. Try it yourself. If I make a mistake, wouldn't be totally unusual. I always kind of do these questions a couple times just to make sure I got all my numbers. And like I said, I write these numbers down as I go. Make sure that you're not gonna, a lot of this is bookkeeping, just keeping track of these numbers because they're so precise. So the total mass of lithium-7 would be these two values added together. I believe it is 1.17174 times 10 to the minus 26 kilograms. So this is my total mass of my parts of my nucleus. So this is the mass of the parts. So if you were building a nucleus, you would pull out 3 protons and 3 neutrons, and they would weigh this much before you put them together. Once you put together the nucleus, it has this mass. So you can see we have a mass defect. We can see that we've lost a little bit of mass here. So in the end, the difference in mass, whoops, not the difference in energy, the difference in mass will be the mass of the parts, subtract the mass of the nucleus, and I'll cheat a little bit and I'll just do it. But I feel like if I've done this correctly, it is 6.704. I think we're given like 5 significant digits here. So I'm going to go 6.7046 times 10 to the minus 29 kilograms. If anybody really wants to check my significant digits, I'll say I'm probably pushing it here. I probably don't have that many significant digits because I did a subtraction, but we won't get into that. Let's just be more than precise, I guess, and we'll carry all those digits through. So I got 6.7046 times 10 to the minus 29 kilograms. That is my mass defect. That is, again, just like it sounds, the defect or the missing mass between the parts and the total nuclei. Now, assuming I got that much right, we now need to find the binding energy. And the binding energy, according to Einstein, and who are we to question him, is related to that mass defect through his famous equation E equals mc squared. So we've done all the hard parts so far. The mass defect, or the difference in mass between the parts of the nucleus and the nucleus itself, was 6.70464 times 10 to the minus 29 kilograms, multiplied by c squared 3 times 10 to the 8th squared, and we get the energy in kilograms times meters squared per second squared. So this is going to be in joules. And we get 6.0341. We'll go with our 5 significant digits again. I guess that makes this a 2. So 6.0342 times 10 to the power of minus 12 joules is the binding energy. Now, important to note that on a macroscopic scale, in our everyday life scale, not a lot of energy is being created or lost or converted, let's put it that way, between mass and energy. Not a lot of mass involved, not a lot of energy is involved. But this is the atomic level. So these are somewhat significant on the atomic level. And if we want to harness the power of the nucleus, even this small amount multiplied by a large number of nuclei, could amount to a large amount of energy. And we'll talk more about this later on when we look at other nuclear processes. But nuclear energy, when we look at the number of joules, you might think, oh, there's not much there. But again, if you can multiply that out by 10 to the 23rd, 10 to the 40th different nuclei, it starts to add up to significant amounts of energy. So one thing I would, if you want to do a little thought experiment, imagine in Einstein's E equals mc squared equation, what if we could cause a nuclear reaction in which we convert even 1 kilogram of mass into energy? Consider the amount that you get. How much power would you end up with? How much energy would you end up with? Would it be enough to I don't know, sustain you for one day? Would it be enough to power your car across town? Would it be enough to generate enough electricity for a small town, maybe a city? How long would it be able to sustain that? I think you might be shocked if you look at the amount of energy that we could get from nuclear energy. And that is the real appeal of nuclear energy, is for a small amount of mass, you will end up with a large amount of energy. So again, just in summary, we have this whole idea of mass being converted to energy and vice versa. And this happens in nuclear processes, whether we compare the mass of the parts of a nucleus. So here's a bunch of parts of the nucleus that we then put together to make a large nucleus. But we can also think of the flip side of that. What happens when a nucleus spontaneously, or maybe we force it to happen, what happens when a nucleus breaks apart spontaneously? We get this alpha particle with a bunch of kinetic energy. We get the nucleus with some kinetic energy as well in this recoil. And so the energy that's being produced here came at the cost of the mass that was, well, I'm not going to say destroyed, the mass that was converted into that energy. So conceptually, probably not what you wanted to hear. It's definitely not something you've heard through your whole career as a science student, because you've heard of law of conservation of mass, law of conservation of energy. But once you get your brain past that, then calculations involving mass defect and binding energy are generally pretty straightforward.